My name is Aaron Toponce. I am on the system administration team at X-Mission. Just came down from work. We're downtown Salt Lake. I actually live in Davis County, so I'm a good drive away. Probably an hour and a half one direction. That's all right. I started using Linux with Red Hat 9 or Red Hat 7, maybe. Red Hat Linux, not Red Hat Enterprise Linux. Maybe in Red Hat 6. I just newly married. We were at USU. My wife was finishing her education degree. We bought this computer, had Windows 98 on it, I think. And I purchased this software box for 40 bucks called Red Hat Linux. And I'm like, I've heard of this Linux thing. I should try this out. So I put in the CD. I thought you installed it like any other regular Windows software, not realizing that I just wiped the Windows OS off of the computer. So I was kind of baptism by fire. But I've been using it since. I graduated from Weber State University with a major in mathematics and a minor in computer science. I had every intention of going to grad school to becoming a legitimate bona fide cryptographer, but family things and just life kind of became a higher priority than grad school. So I never pursued that avenue. I may eventually. In fact, I recently started studying for my GRE, thank you. I was going to say the GCAT, not the GCAT. The GRE for mathematics. So refreshing on my calculus and abstract algebra. So we'll see how that goes. I'll be presenting on random numbers. First, I want to apologize for last month. When James emailed me, I think in May-ish, maybe April, he asked, does it have a timeout? He asked if I'd be willing to present in, to plug. There it is, we're good. And I said, absolutely. He said, June, July, or August. And I said, well, let's do June. So he said, all right, June 19th, it's a Tuesday. Sounds good. I put in my phone Thursday, June 21st. So when he emailed me, like it was like 7:03, are you coming to plug? And I'm at home hanging out with my wife and daughter. I'm like, God, really? No, it's in 2 days. I've been looking forward to it. So I feel bad. So I bought Krispy Kreme donuts. Take advantage of it. That's my, I'm sorry.
All is forgiven.
Thank you. But it's funny, I was telling James, took a family trip to Washington, D.C. for the 4th of July. And we came back Thursday the 5th, and my heart stopped thinking that the meeting was on the 3rd. So I checked my phone, and oh no, I've got a couple weeks. And the weekend hits, and I get nervous about it. Needless to say, I've been very carefully watching the calendar this month. So I was even here at 6 o'clock. All right. So I'm going to talk about random numbers. This is a presentation I give, I guest lecture at UVU as well as University of Utah in their computer science department, their information security classes. So this is a presentation that's kind of in flux. I get feedback from the students, feedback from the professors, and I kind of modify it and change it. I'm not going to talk really much about Linux, actually. I know this is a Linux group, but everyone did their Linux introductions. That's all the Linux we're going to get. We're going to do some math. We're going to do some computer science. We're going to be theoretical. We're going to be practical. I'm not going to make this too terribly difficult. But if you do have questions, feel free to ask. So the kind of the whole goal of this presentation is to talk about secure random numbers rather than just the Dilbert cartoon where you've got the little guy going 999999, right? Or the XKCD cartoon where in the source code it says random number equals 4 and it was chosen by a fair dice roll. No, I'm actually going to talk about how we can use this, how we can use random numbers securely. And when I'm saying that, I'm leaning towards cryptography. We use random numbers all over cryptography. In fact, they're really kind of the foundational building block. If you can break the random number generator in a cryptographic primitive or in an application that uses cryptography, you can usually end up breaking the entire stack. So we see it in symmetric ciphers. We use them for generating random keys, like AES keys. We also use them for generating initialization vectors. They're just random starting points to put the cipher into. Because without that, all the ciphers would start at the same spot all the time, right? AES would always start in the same location. So this is just kind of a random location to start at before the cipher gets going. Asymmetrically, we use them for generating prime numbers if we're going to do modular integer factorization, like an RSA or Diffie-Hellman. We need large primes. We need them chosen randomly, so we'll use random numbers there. In elliptic curve cryptography, we have a curve defined for us, and we want to pick points randomly on that curve, so we'll use them in that regard. And then in hashing functions, if you're hashing a password, for example, storing it on your authentication servers, salts are a way to get past rainbow tables, which is a valid attack for attacking password hashes. So salts are just a random string that you append to the password before it gets hashed. So the hash isn't always the same for the same password, right? As long as that salt is different, that hash will be different. So we use it through the whole entire stack. In terms of what makes a secure random number generator from just an insecure one, I put the secure properties in red. Generally, we like our generators to be fast, which I'm speaking relatively, right? I request the number, I should be able to get it back. I shouldn't have to wait. But that can depend on your load, obviously. If you're a high load HTTPS server, you'll need to be generating random numbers quickly. A low load, obviously you won't. But we want them when we request them. High quality is kind of a loaded topic, kind of a buzzword. But we definitely want them to be uniform. I don't want any sort of bias in my random number generation, my output. Every number should be equally likely as the next, in other words. We're going to talk about statistical tests, but they should pass a whole suite of statistical tests. In theory, I can say, let's put up this equation. If I were to apply random numbers to it, this would be the properties of the output. Now let's throw the generator at it and see if it lines up, basically, right? And we have a whole ton of tests we can try. Dimensionally equidistributed, this is kind of a controversial topic. When you think of generating random numbers, you think of getting them one at a time. I want a random number, here's 4. Give me another random number, here's 128. But what if I wanted a random XY coordinate? Then I want 2 random numbers. And now I'm no longer interested in just the uniformity of the X values, but also the Y values. I need uniformity across 2 dimensions, right? And we can extend that out to n dimensions, 3 dimension, 4 dimension, 5 dimension. So that's what that's talking about. And then independent just means that there should be no clear mathematical relationship between the current random number and the next. Now granted, in pseudo-random ones that we're generating in software, there's a mathematical relationship. And that's what those tests are for, to say, well, okay, there is a dependency from the previous number to the next, but it still passes this suite of tests, so it's okay, right? But I shouldn't be able to say 2, 4, 6, 8, 10 and say, oh, my random number is just the next even number, right? That's not very independent. We're just adding 2. All right. We like them to, if they're pseudo-random, to have long periods or long cycles. So we'll always start at a certain spot. We call that the seed, right? The seed is my initial starting point. And then we send it through the software algorithm, and eventually it's going to get back to that same number, which means that we're just going to follow that cycle. We want that cycle to be as large as possible. And we'll see some that have some exceptionally large cycles. So they're, for all practical reasons, they don't repeat. Okay? And then trustworthy. We'll see one example of a backdoored random number generator, which is kind of entertaining. But we should be able to rationalize every decision we made behind the design of the algorithm. So these are all just insecure random number generators. To make them secure for cryptography, we need to add 2 more criteria. And essentially, it's we can't predict the output with any better probability than pure random chance. Okay? And if the state of the generator is compromised, we can't regenerate past states. Okay? So in the case of the prediction, if it's generating random bits, 1, 0, 1, 0, 0, etc., I should not be able to predict the next bit with any better probability than 50%. Right? It's 50-50. I just, no matter how much output I've analyzed, I cannot get an upper hand on what the next bit will be. That's an absolute requirement. And then, like I said, if we compromise, an adversary compromises the state of my generator, reads the memory, can see what the current state is, and now can observe all future output, still can't reconstruct past output. Right? It can only go from here forward. We can't go backward. If those two are met, then we have a secure generator. So here are some of the statistical test libraries for testing random number generators. Mike, you might want to move to that chair. Yeah, right? OK. Die-hard was first introduced in 1995. There are a few names in the world that are experts in their field, right? Einstein, for example, in relativity, or Tesla in electricity. I'd say Elon Musk, but he's kind of on my bad list right now. But space exploration, I'll give it to him. When it comes to random number generators, and I'm not sure how to pronounce his last name, George Marsaglia from the University of Florida is that guy. And his name will pop up a few times in my presentation. But he created this suite called Die-Hard. It has 11 mathematical tests. And if it passes those tests, then it's a good generator, right? Well, another mathematician a bit later, Robert Brown, created an update, essentially, to Die-Hard. And following the Bruce Willis films, called it Die Harder. Okay? That's legitimately why he chose it. He took the 11 tests from George Marsaglia's paper and added 20 more. Realized that there were a lot of nonlinear tests that George Marsaglia had not looked into that could be added, that added value to testing random number generators. And then in 2007, a couple of French mathematicians completely reworked the entire suite. Rather than build off of Die-Hard or Die-Harder, came at it from scratch and created two tests, one called Small Crush, the other called Big Crush. Big Crush actually takes hours to complete. In most practical purposes, Small Crush is sufficient to test your generator. But if you've got cycles and time to burn, and you really want to nail down the quality of your generator, then Big Crush is what you're after. But there's over 100 tests between those two suites, mathematical tests that get applied. Here's just a few. This is just a very basic handful, right? A frequency test is a simple uniform check, right? If I'm generating numbers between 1 to 10, then each one should have a 10% chance of being generated. So if I generate 100 random numbers, on average, I should see 10 1s, 10 2s, 10 3s, right? So forth. So that's just all the frequency test is, just testing how many of each number in my range that I'm getting. And I should see a pretty flat, uniform distribution. Serial test is testing a sequence, 0, 0, 0, 1, 0, 2, or 2, 3, 2, 4. We could go 3, 4, 5. We're just testing how the sequence falls. I'm not interested in looking at 3, 5, but I am interested in looking at 4, 5 or 3, 4. We have a poker test, which is looking at poker hands, straight, full house, these sorts of things. And a gap test, testing gaps between zeros or between ones. There's no gap between 0, 0, for example, but there's a gap between 0, 1, 0. I have a gap of 1. So we're not interested necessarily in the number itself, but how many gaps I see, as I request each number. One of my favorites is a Monte Carlo simulation. This is simulating pi. We're all familiar with pi, right? It is the ratio of what? Almost. Diameter. Circumference of the diameter. Yep. Very simple. Well, if I were to take a unit square and inscribe inside the unit square the unit circle, okay, the area of that unit square, the unit circle to the unit square is pi. Okay? I mean, it's just by definition, the ratio of the circumference to the diameter. This is just looking at a quarter of that. But if I were to generate random xy coordinates and plot them inside of that unit square, and then count the coordinates inside the circle versus outside the circle, the more points I plot, the closer it should approximate the value of pi. And if it's completely continuously filled in, it is pi by just the raw definition. So this is just one example of a Monte Carlo simulation. We see Monte Carlo simulations in predicting weather. We see them in using, say, the Social Security Administration's death rate, like how old people are living, so I can simulate when someone's going to die, basically. We see them all over the place. Derek, do you have a question?
What is a Monte Carlo simulation?
All a Monte Carlo simulation is using a random number generator to simulate a real world thing, right? An applicable thing. If I wanted to simulate, for example, what effects construction could have on a certain exit off of I-15, right? I can use a random number generator to randomly generate when cars will be approaching that exit, maybe how many as well, and then I can see, maybe estimate by that what congestion would look like, maybe accident rates, that sort of stuff.
So it's a methodology more than...
Right, right. And with Monte Carlo simulations, you apply, if you can, thousands or tens of thousands of simulations, right? And you group them all together and say, as an average, this is what I'm seeing, right? So here's another example. Utah, most of the state is Mormon, right? There's a leader of the church, and there's 15 leaders, and the oldest one is always the prophet. And in seniority, right, based on when he was put in that position in the 15. So the oldest one who outlives everybody else gets called to be the head. But I know all their ages, like I know when they were born, and using the Social Security Administration death rates, I can predict what year they would die, and then using those predictions, see what the probability is of when the next person in line would be the next prophet. Right? So I can say, oh, I think Russell Nelson is the current. I could say with great probability that Dallin Oaks will be the next one with 15% on this year, and it dies off to 12 and 11 and 10, just based on these death rates. Right? That's a Monte Carlo simulation applied to who's going to be the leader of the Mormon Church. Simple? All right. This table shows testing results of various pseudorandom number generators. Don't get caught up in what these algorithms are, but instead this is rated by overall failure rate. Well, and the time it takes to calculate the random number. So the higher up we are on the list, the better, the higher quality the random number generator is. What's interesting is this is showing what these statistical tests, the results look like. We can see for most of these, we see some failures. Overall, 58 failures. These are running against that test U01 suite by those French mathematicians. Okay, so we're seeing failures to Big Crush, I think is what he tested. But so we're seeing some failures in certain areas, and they increase. But as we come down here to XS add, we can see all of a sudden we jump by 10 times in the overall failures, and we have some systematic problems, meaning it's always failing in this test in the same way. Where in here we're not seeing systematic problems, but we're seeing them here. In the case of MT19937, the Mersenne twister, which I'll talk about, always fails in the linear comparison test. And we see that with well 1024A. So it's just showing what these failure rates look like, okay? So obviously the lower the failure rates, like Zorro, Shiro, 128 plus, has very few compared to these guys at the bottom. And further, this is nanoseconds per 64 bits. So it's timing how long it takes to generate a 64-bit number. We can see that for Zorro, Shiro, 128 plus, 0.87 nanoseconds per 64 bits versus 2.66 nanoseconds for Mersing Twister. So it's a better performing one, not only statistically speaking, but in terms of just raw performance generating the same amount of numbers. All right, setting that aside then, let's break down random numbers. When you think of random numbers, you probably think of one of two things: true random or pseudo-random, right? True random is something that exists in nature. Somehow we are able to collect the data out of nature and get a random number out of it. Like the common example is radioactive decay. I have some sort of radioactive source, like maybe out of a smoke detector, put it under a Geiger counter, and it counts when it detects particle decay, right? That's a true random number generator. Versus these ones we were just talking about are pseudo-random. They're strictly designed in software. They're fully predictable if you know the starting seed, right? But it's not so simple. That's fine, but we can have secure pseudo-random generators. Okay, these are generators that are suitable for cryptography, and we can have insecure true random generators. In other words, true random out of nature that would not be suitable for use in cryptography. Kind of mind-blowing. So it's really a 2x2 matrix, if you will, a quadrant. So we can look at security on the rows and then whether or not it's true or pseudo in the columns. And I'll break all these down as we work through. So let's talk about insecure pseudo-randomness. I've broken these down into two subcategories: mathematical and algorithmic. Now, I know I'm probably splitting hairs. A software algorithm is really just raw math, like I got it. But I'm drawing the line at where I can't easily do an algorithm on a calculator, right? I can't punch in a for loop or an if conditional. I can't punch in like bit shifting in a simple calculator. But I can do add, plus, and divide, and square roots, and that sort of stuff. So that's kind of where I'm drawing the line. All right, if I can punch it into a scientific calculator, I'm going to call it mathematical. If I need for loops or if conditionals or variable assignments or arrays, I'm going to throw that on the algorithmic side. So some algorithmic generators. You may or may not have heard some of these. Linear feedback shift registers. You're basically just doing bit shifting in an array of bits, essentially. They're an algorithmic, insecure, pseudorandom generator. Mersing Twister, by far the most popular, most famous pseudorandom number generator out there, is an insecure one. There's some new ones that have kind of come out that are a family of generators rather than just one generator itself. And these are the PCG family, Well family, and XOR Shift family. If I were to pick a favorite out of those families, it would be the XOR Shift family. High performing, awesome statistical tests, meet everything we need for insecure pseudorandomness. Good high quality generators. Mathematically though, cellular automaton, I can do cellular automaton in a calculator. Cellular automaton is basically just life simulations with pixels, essentially, right? So I create some rules and I say, this cell is a life, and based on where the proximity of other cells of life exist will determine if it lives or dies, grows or shrinks, how it changes.
Conway's Game of Life.
Like John Conway's Game of Life, precisely. A more simple one would be Stephen Wolfram's singular cellular automaton. John Conway's is two-dimensional, an X and a Y, right? Stephen Wolfram created a one-dimensional where we just look at strictly a linear, like side-to-side growth. Chaotic maps, double pendulum, really anything that we can mathematically compute in chaos If you've taken differential equations, some of these might be familiar. You do a lot of chaotic stuff in differential equations. The lagged Fibonacci generator, linear congruential generator, I'll look at these. All these can be done mathematically. The very first one, the very first piece of software that was written to generate random numbers was by John von Neumann in the early 40s. Here's another one of those names that you just can't escape. He's the father, if you will, the big guy, the head honcho of computer science. He's written more, had more influence in computer science, I think, than most can say. But he created this middle square method, and it's really simple. You start with an n-digit seed. Remember, the seed is just the first number we start the generator off in our cycle. Start with an n-digit seed, and you square it to create a 2n-digit seed, and then you take the middle n digits out. So for example, if I started with a 2-digit number, I would square it to create a 4-digit number, and I may have to add zeros in front of the number as necessary to make that 4 digits work. And then I pop the middle 2 digits out and go again. Okay. It worked fine in the 40s, and if you pick a large digit number, like say a 10-digit or a 20-digit number, this actually will hold out pretty well for most basic use cases. But it does have some problems. It fails practically every randomness test that we've developed. It has really short cycle length, and depending on the number, well, not depending on the number, it is biased. Here is a connected graph, directional graph, of every 2-digit number following this algorithm. Okay? So if I pick the number 54, squared it, I don't know what it is, and took out the middle 2 digits, I would get 91. Square it, take out the middle 2 digits, I would get 28. And I would work my way through. Like I could probably start here. 8 squared is 64. That would be 0064. The middle 2 digits are 06. Squared is 36. Middle 2 are 03. That's 9. The middle 2 are 000, right? So middle 2 are zeros. So what happens with 0 squared? It just sits on 0. But what's interesting is because I picked 54, I will never ever generate 17. I'll never generate 38 or 87 or anything in the red, green, purple, or yellow, right? That's that bias that I'm talking about. Like every 2-digit number should be equally likely as the other, but that's not the case with this method. Now, John von Neumann was aware of that limitation. He was a brilliant mathematician. So like I said, he picked large ones. He did pick 10, 15-digit numbers to work with this. But what he liked about this and why he preferred it is when it fails spectacularly, right? When I hit 0, it's 0. There's no question about it. The random number generator is over, right? In fact, he's famous for quoting saying, and I'm paraphrasing here, but anyone who thinks they can generate randomness from a computer is in a state of sin. And that reflects his philosophy in that regard. The linear congruential generator came out a little bit later in the 40s, and it was its first real attempt to address the bias that the middle square method had, while also providing, a complete and total uniformity and maximizing its cycle length. Do you guys remember how to find the slope of a line from algebra class in high school? Y equals what? Mx plus b, right? Piece of cake. That's all this is. That's it. The only difference is we have a modulus on here, and a modulus is just a cap. So if I say, like, if I did random 24 hours in the day, I said mod 24, the number can never get higher than 24. Cool? So this is just y equals mx plus b. I'll change the variables. It's nx plus 1, the next output, is a, that's our m, times the current seed, which is our x, plus c, there's my b, mod m. Okay? We do have some requirements, and they're listed here. If I want a uniform generator that maximizes its cycle length, then these are the 3 requirements I need. C and M have to be coprime. Anyone know what coprime means?
They don't share any multiples.
Correct. They do not share any factors or any multiples.
Any
Yep.
factors, that's it.
The only factor they share is 1, essentially. So in the case of like 20, right, I know that I've got an odd numbers in there, but if I picked 20 and maybe 7, right, there's no common shared factors between those two digits other than 1. So that's all that means to be coprime. C and M have to be coprime. Then A minus 1, whatever A is, subtract 1 off of it. It has to be divisible by all the prime factors of M. Right? The prime factors of n are reducing all my factors just down to their prime factorization. Right? So in the case of, let's say, 8, what are the prime factors of 8? 2. Yeah, easy. What about 10? Another easy one. 2 and 5, right? Pick a harder one. How about 12? Wait. 3 and 2, right? Not 4. Why not 4? Because it's just more 2's, right? So the prime factors are 2 and 3. Okay. And then if a minus 1 is divisible by 4, or pardon me, if m is divisible by 4, then a minus 1 must also be divisible by 4. All right. Let's look at an example. Random 24 hours in the day. Okay. I picked C as 5 and 24 as m. Are they coprime? C and M coprime. Yes. The only valid factor they share is 1. A is 13. The requirement was that a minus 1 must be a multiple of all the prime factors of, in this case, 24. What are the prime factors of 24?
2 and 3.
2 and 3, right? Okay. So is a minus 1, 12, is 12 a multiple of 2 and 3? Yes, okay. And then is 24 divisible by 4? So is a minus 1 divisible by 4? Yep. So this should give me all 24 numbers possible. And it should be unbiased. So I picked a seed of 3, work through the numbers, and I get 20 as my output. We'll see if that's true. 3 times 13 is 39. 39 plus 5 is 44. 44 minus mod 24. 44 is too big. So I subtract 24 off of 44 to get me within the range. That's 20. So 3 brings me to 20. Right? Make sense? You have a question?
So yeah, you're somewhat random, but once you hit a number, you'll never see it again in the cycle.
Right, yeah. So it's uniform. Every number is equally output, but it's predictable. Yeah, once I know where I'm at, I know what my feature output is for the rest of the way. Yeah. And for a lot of random numbers, predictability is okay. For cryptography, it's not, obviously. But in some situations, it might be all right. All right. Then in the 50s, we said, you want to know what? Let's try and get a period, a cycle length, that is bigger than its modulus. That was mod 24. It only gave me 24 valid outputs. But could it be possible to get an insanely larger cycle length than the modulus itself? Turns out, yes. And here is a valid approach called the lagged Fibonacci generator. Another math question. I told you it's going to be math, but easy. Do you guys remember your Fibonacci sequence?
1, 1, 2, 3, 5, 8, 13.
21, 34, 55. Yep. So the Fibonacci sequence takes two numbers, two seeds. We sum those together, right? Like 1 plus 1. There's my seed A and seed B. That equals 2. But then my seeds change. Now this becomes A and that becomes B. So 1 plus 2 is 3, right? And we continue this sort of shift where I come up with this sequence. 21, 34, 55, etc. Okay? The lagged Fibonacci generator is exactly this, except for a couple minor differences. First off, we're starting with 2 numbers, exactly 2, in the Fibonacci sequence. They can be any 2 numbers. I don't have to start with 1 and 1. That's the traditional standard textbook one. But I could start with 1 and 3. or 4 and 6, right? I could start with any two numbers. The lagged Fibonacci generator, I'm going to create an array or a list of numbers. Let's say a list of 8 numbers. So we'll say A, B, C, D, F, G, H. Okay? 8 numbers in my list. And I'm going to go ahead, and I put this star here. This star can be any binary operation, addition, multiplication, subtraction. This is the exclusive OR operation, not the exponent operation. Okay? The exclusive OR operation is a bitwise operation. I'll leave it at that. Okay, let's just stick with addition. So I say, well, I'm going to pick what are called lags. I'm going to pick the jth lag and the kth lag, and I'll sum those together. Let's say that I wanted to pick that one, and that one is my lags. Okay, this is lag j, the cth element, I guess the third element, and k, the 6th element. These are going to be my lags. So we'll just, for fun, let's create some numbers. We'll just do 1, 2, 3, 4, 5, 6, 7, 8. All right, so I'm going to go ahead and I'm going to do addition. So I'll say the jth number, which is 3, plus the kth number, which is 6, mod m. I'm going to pick, we'll do 24 again. Okay. So 3 plus 6 is 9. 9 mod 24 is still 9. So now what we'll do is we will append this to the list. We'll push it on the stack, as you would say. And then we're going to pop off the first element. But the j was my third lag. My j lag was my third element, and the k was my 6th. That means j is not pointing at 3 anymore. J is now pointing at 4. And k is now pointing at 7. That make sense? So we're just slowly shifting the array, or my list of numbers, to the left. I'm always doing the operation. 4 plus 7 is 11. 11 mod 24 is 11. So 11 gets added. 2 gets popped off. And then I get j and k repointed to their new positions. And we continue in that manner. Make sense? The only requirement is, well, there's 2. I missed one here. Obviously, I need at least k elements. If I'm going to pick the 6th element in my operation, a 5-element array isn't going to help me. Right? I need at least 6. So I need at least k elements. But second, the element at or before k, one has to be odd at least. If I end up with a strictly even array, what's going to happen with my... It stays even, right? But if I have a strictly odd array, at least I'm guaranteed odd or even, right? 2 odds always make an even. An odd and even will make an odd. So those are really the only 2 requirements. These are the sizes of the periods. Suffice it to say they're much, much larger than the modulus, significantly larger, okay? 2 to the k minus 1 times 2 to the m minus 1 in the case of addition or subtraction. Here's a visual of that kind of shift, right? This case, I'm choosing the 2nd and the 8th, and I chose to do the exclusive OR. So that becomes the output. The output is appended to the array. The first element is popped off, and then we go again. Appended to the array, popped off, and we go again, right? And just continue in that manner. Cool. Then finally, in terms, oh no, I got 2 more. Mersenne twistor and the XOR shift family. Mersenne twistor came about in 97. Yeah, that's right there on my slide. Should read my slide. 1997 by a couple of Japanese mathematicians. And they knew the current state of generators. For the most part, they were OK, but they thought they could do better. Mersenne twistor is based on what's called a Mersenne prime. And all a Mersenne prime is I take a prime number, let's say 3. Okay? I raise that I take 2 and raise it to that prime. So 2 to the third is 8. And then I subtract 1 off. That's 7. If that result is also prime, then that's called a Mersenne prime. So 7 is a Mersenne prime because 2 cubed minus 1 is still prime. Okay? Turns out 2 to the power 19,937, which is a prime number, minus 1 is also prime. So that's why it's called the Mersenne twister, because it uses, the cycle length is that of that size, okay? Which is insanely huge, massively crazy large. Like AES 256 is a 256-bit cipher. That's 2 to the 256. This is 2 to the 19,937. Okay, 2 to the 257 is twice the size of 2 to the 256, right? So you can just see how much crazy, insanely large this is. This is stupidly big. It really, it's, yeah, it's just dumb. I'm just gonna put it that way. But it is unbiased. What's interesting is we talked about, remember my slope of the line, y equals mx plus b? It uses that algorithm as a mixing function as part of its algorithm to create this algorithm as a whole. It uses the linear congruential generator as part of its mixing function. It's unbiased, it's fast, it's got a huge period length, and as we saw earlier, it passes a whole suite of randomness tests. And it's in most programming languages. It's in a lot of software. It is by far the most widely deployed random number generator out there. Okay? It just is. However, pardon?
Is it used by Linux? What is Linux?
For the kernel space generator,
Yes.
I'll get there.
Oh, okay.
It does not use Mersenne twister though. Mike.
So, fact about that number, it's 6,002 digits long in base 10.
6,200 digits in base 10.
6,002.
6,002, yeah. Nice. Yeah, it's just big. Do you have a question?
Twister was non-secure on your
Correct. Correct. I haven't reached any secure ones yet, suitable for cryptography. Yeah. The problem with Mersenne twister is once I have examined enough output, I can predict all future output. Right? That fails my security test. Another problem also is going backwards. If I compromise the state, I can work my way backwards through the generator and get all the past states too. So yeah, it fails. And the same with this XOR shift family. So this was created by initially created by George Marsaglia. There's that name again. He'll come up again. In 2003, he wrote a paper on how we could just use the XOR bitwise function and the bit shifting to create a pseudorandom number generator. Nothing else. No addition, no modulus. All we have to do is XOR two numbers together and shift them left or right, some number of bits, and we're done. Right? Well, this Italian mathematician, Sebastiano Vigna, if anyone speaks Italian, I would really be interested in learning how to pronounce his last name, expanded on his paper. He said, we can do a lot with this, actually. So he created this whole XOR shift family of pseudorandom number generators. And that table that I showed you from the beginning on the statistical tests, that comes from his website, actually. He does a pseudorandom number generator shootout where he tests all these generators and pits them against each other and shows how well these XOR shift based generators perform. And they are high quality generators. They are the fastest generators out there. They have a maximum period. We'll look at that in a second. They're totally unbiased. They pass the most statistical tests with the least amount of failures. And what's crazy about this is, that's a typo, XOR shift 128 plus is now implemented as the math.random JavaScript function in every major browser. iOS, Apple, Microsoft, Android, Linux, Opera, Edge, Firefox, Chrome, Safari, Conqueror. I'm not joking. And this is, I'll show you why in a second, but this is the source code. This is the entirety of the generator. It's really, really stupid simple. So we're going to generate a 64-bit array that holds 2 elements. That's it. Okay? So we're keeping 128 bits of state. That's all we're doing. And then you'll notice the comment here. It must be everywhere not 0. That is the only failure case. If both elements in S are 0, then the generator will always be 0. I'll just get nothing but zeros as the output. So as long as I have something that is not 0 in that array, we're good to go. Then I'm going to create 2 temp variables, x and y, and I kind of shift them around a little bit. But I assign x to the first element and y to the second. Okay, these are just my temp variables. And then I'm going to reassign the first element to y. So at this point, S is now, both elements are identical, right? They're the same thing. But I'm going to reassign the second element based on a lot of stuff. And that's this here. I'm going to say x equals x XORed with itself, bit shifted left, 23 bits. And then to do the assignment, I do all this XOR and this other bit shifting, and then put that in the second spot. And then the output the number, I output the second number plus my temp variable y that I assigned earlier. And that becomes my 128-bit number. That's it. Like the Mersenne twister is a full page of point size 12 font C code. Like this is remarkably cool. So why then? Why did all the browsers go this way? Well, in December 2015, some guy noticed, I think it was actually a little bit earlier, November, October, was testing the generator and noticed that the output wasn't exactly what it should have been. So he created a monochrome, pixelated random image. And I'll show you that in a second. And sent it to Google and said, your generator sucks. Fix your generator in Chrome. And so in December 2015, the V8 JavaScript virtual machine replaced the generator, which was multiply with carry 1616. I'll give you one guess as to who invented multiply with carry. George? Yeah, the guy with the hard name. Yeah, George Marsaglia, the University of Florida dude that created Die Hard and that also generated the XOR shift family. He pops up. Telling it, the guy is a random number generator genius. Anyway, that's what Chrome was using. Well, it turns out it's not so hot, so they replaced it. Here's why it's not so hot. This is that image that he generated. What do you see? What is that telling you?
It's biased.
It's biased, right? Where I see these thick lines, these numbers are more likely to be generated than where they don't exist, right? I have higher probabilities of generating these numbers along this line than the ones in this area there, right? That's not cool. So we replaced it with XOR shift 128 plus, and voila, no pattern, right? This is just a visual check. This isn't to say, aha, it's good. We still need to apply those tests. We still need to, actually analyze the generator. But this is a good spot check, right? If my generator looks like that, I got a problem. If my generator looks like this, all right, I might be on the right track, right? So Google was the first one to put this into V8. And by putting it in V8, anyone who implemented that, which includes all the Blink-based browsers, so that's Opera and Chrome, and all the WebKit browsers backported it, so Safari, the iOS browser, which I still think is Safari, right? Conqueror. And then Firefox came a bit later, and then Microsoft Edge also did the same. So if you're using math.random in JavaScript, know that this is, if you have a modern browser, a modern version, this is what you're using now. So that's good. All right. Let's move away from insecure and go into secure pseudorandomness. So now things change a little bit. When we talk about secure pseudo-randomness, because they're pseudo-random, they're all going to be based on algorithms, software algorithms, but they're going to meet those last two requirements, which I'll cover here in a second. But we can do these really one of a few ways. We can base them on block ciphers, and we have some standards where that's the case. These are like, a block cipher is like AES, or two-fish, or blowfish. You've probably heard of some of these. Those are standard block ciphers. We can base them off of stream ciphers, and here are some other standards or implementations that are based on stream ciphers. RC4 is a stream cipher. Cha-Cha-20, may have heard of it, also another stream cipher. We can base them on hashing functions. We could base them on SHA-1 or SHA-2, so there's a couple standards there. Or we can dig into the raw math. And we can take advantage of what are called trapdoor functions and build custom, not necessarily based on cryptographic primitives, but mathematically secure algorithms. And so some of those are listed there. Actually, I need to fix this because DevURandom and CryptGenRandom are based on cryptographic primitives, but they do some weird stuff, so that's why I threw them there. So let's remind ourselves, to be cryptographically secure, if I'm looking at the bits that are coming out, okay, I cannot predict the next bit with any greater probability than 50%. It is just pure random luck on whether or not I get the next bit correctly. Okay? Then, if an adversary successfully compromises the generator, they can't reproduce the past states. Why would that be important? Why would not being able to reproduce the past states be important?
If you can reproduce back the past states, you could go back and have information to break ciphers that we're using before.
Okay, yeah, so if I could generate the past states, I could use that information to break the previous ciphers. Mike?
If you've recorded communication, you can potentially then go backwards to know what this, or previous states are and see what it is.
Right, yeah, so I think you guys are saying the same thing, that I can basically, if I know the past states, I could regenerate past keys, and then I could potentially use those keys to break past communication. Yep, TLS sessions or whatever. So that's why it's critical. We call this prediction resistance, and in the case of satisfying what's called the next bit test, not being able to predict, prediction resistance. And then withstanding a state compromise, there's two terms. If you go the government route, they call this backtracking resistance. This is a term that NIST uses. But if you talk to cryptographers, they refer to it as forward secrecy or perfect forward secrecy. You might have heard that, right? Where every key that gets generated is entirely ephemeral, completely temporary, and fully unpredictable. Okay, so I can't get the past keys. So let's look at some mathematically sound, and we'll move into some other designs. So this one is my favorite, like my favorite of all the favorites. Blum Blum Shub. I just like the name. It was designed by husband and wife, Manuel and Lenore Blum, and then their friend Michael Shub, all brilliant mathematicians. I want to say they're from Chicago. Don't quote me on that. But designed this in 1986. And they based this on what's called a trapdoor function. A trapdoor function is where I can calculate it very easily, but going backward is very difficult. And it turns out integer factorization is one of those things. I can multiply two big numbers together relatively painlessly. But if I have that composite and I say, give me the factors of that number, that's kind of problematic, right? The naive way would just start with, well, let's divide by 2. Is it divisible by 2? Is it divisible by 3? Is it divisible by 4? And just kind of work our way up. There are more efficient algorithms, but it's essentially searching, and it sucks. Well, if I get big enough numbers, it turns out this problem becomes too difficult to solve in practical time with practical hardware. Okay? If you've heard of the RSA encryption algorithm for public and private keys, it is based entirely on this principle of integer factorization. We take two big giant prime numbers and multiply them together, and that output becomes the public key. The secret key is derived from it, but if I ship that off, that key is big enough to say, it's too difficult for you to find those two prime factors. You'll be at it for centuries before you get anywhere. Okay? Well, Blum-Blum-Shub is based on exactly that. I take a seed and square it, which is itself multiplied by itself, mod m. However, that m is based on two primes, p and q. Okay? So I take two primes and multiply them together and get this composite m. Why primes? Why not, say, two other composite numbers? Any ideas?
Because just like you described, if you start the naive way, divide by 2, divide by 3, if P and Q are not prime, you have a much quicker route to them by that naive process.
With P and Q, there are only two factors, right? And it's P and Q. There's no more. But if I picked two composite numbers, I have more than two factors out of m, right? Like if I did 4 and 4, that's 16. But that's a bad example. Let's do like, let me think here, 12 and 20, right? 12, I know I've got 2, 3, 4, and 6. 20, I know I have 2, 5, and 10, right? I have all these numbers that can factor out m, the result. But when I've got, but when I've got primes, it's exactly two numbers.
So seed squared needs to be larger than m. Otherwise, you're just always going to be seed squared, right?
No, not necessarily. If I start with 3, and this modulus is some 6,000 digit base 10 number, this will be 9, but then 81, but then, and it'll grow pretty quickly until we bump up against that m. All the time. Yeah, so I might.
For each new number.
Yeah, for each new number. So I'll give you an example here on the next slide. But I have, some max, right? We call m, which is p and q. So I know that my squared function looks, something like this. But as soon as I hit that m, I'm going to drop somewhere down here and continue the cycle. Right? So it's okay that x is smaller than m, because eventually I'm going to hit it. It's just important that I stay within this range and don't go outside. So the only requirement is that my initial seed must be co-prime to m. We've learned what co-prime is. And then we have a special requirement with p and q. These last two basically just say it needs to be a safe prime. And what a safe prime is if I divide it by 4, the remainder is 3. All that crap right there is all that's saying, right? Divided by 4 and the remainder is 3. So 19. Is 19 prime? If I divide it by 4, what's the remainder? 3. So 19 would be a perfectly valid P, for example. Okay? And then 23, I'm making it easy for you. Is 23 prime? Yeah. What's the remainder if I divide by 4? So 23 would be a perfectly practical Q. So 19 and 23 could work for P and Q. Multiply them together. Whatever that is M. Now my initial seed just has to be co-prime to that result, which basically means it can't be M, it can't be 19, and it can't be 23. Or any multiple of those numbers. So if I pick 7 or another prime number, I'd be good to go. Okay. So here's an example. In this case, I'm doing 11 and 19, and my initial seed is 3. 3 divided by 4 is 3, so we're good. So 3 squared is 9. 9 mod whatever that result is, or pardon me, 11 times 19. Still 9. 9 squared is 81. 81 mod this is still 81. 81 squared mod that now becomes 82. Right? 82 squared mod P times Q is 36. 36 squared times so on. See the result? Make sense? I see some confused looks, so I'll pause. Who has questions?
You actually went through all of these for us? Or
Yeah.
Did you get this all? You went through the math.
Yeah, well, it's just a calculator.
Okay.
3 times 3, 9 times 9, A1 times A1.
My confusion still comes back to, I'm generating a public and private key, and you're saying, well, you're going to keep multiplying your seed. Until when do you stop and say, now I've got a good public and private
Oh, so, okay, so
You're stopping
the public key is the multiplication of P and Q, and that's it. Whatever, your public key is the modulus, whatever that is, right? In fact, RSA Laboratories, they stopped. But to prove the security of this idea, they created what's called the RSA factoring challenge. If you do a Wikipedia search, there's a whole Wikipedia article on it. But they created a ton of moduluses based on P and Q and said, we'll give you $1,000 for every one you solve, right? And so the mathematicians and the computer guys went nuts, and the good starting bulk of them got solved. It started out with small primes, and those primes got bigger and bigger, but it got to the point where now I think the most recent was RSA 220. I was going to say 240, yeah, 220. And we're recommending RSA 2048 for the current standard. And we're working on, what's the next one, Mike? After 220? 230? Okay. And I think there has been some progress, but it hasn't been solved yet. And they stopped giving out the $1,000 rewards. It's no longer available. But anyway, it works. It's a valid trapdoor. The problem with this is this right here. It's cryptographically secure. If P and Q, this is a typo, I was thinking symmetrically, not asymmetrically. If P and Q are 1024 bits or bigger, then this is cryptographically secure. But multiply two 1024-bit numbers together, and then do the x squared mod that number. It's intensive, okay? There are valid algorithms out there, and it's just slow, because if you think about it, your CPU is really good at addition, but multiplication is repeated addition, and exponentiation is repeated multiplication. So when I'm doing something squared, I'm doing a multiplication of that number, which is a bunch of repeated additions. So I'm spending a lot of stupid time on the CPU. I saw a hand. Yes?
So I'm just confused because the fundamental operation is the square.
Uh-huh.
So for any,
Well, yeah, in this case. Mm-hmm.
whenever you hit the mod, you wrap down to a relatively low number.
Depends.
You can very easily predict the output until it hits the mod again.
Maybe.
For example, 9 and
Yeah.
81. Anytime
Yeah.
you hit 9, the next number is 81.
Sure. Because we're operating on, what, 4-bit numbers?
Sure, but I mean, take any P and Q, make them 1,000 bits long. If I start with 9, the next number is 81.
Sure.
Modulus tends to get used more, though, the higher the number. So when you're talking like 20 and 48-bit numbers, I mean, these are huge numbers, right?
Sure.
And you're often like rewrapping into the thing. Does that make sense?
Right, so that's what I was going to get to. And to restate for the camera, I got to remind myself I need to keep restating on the comments because no one else is mic'd up. To restate what he said and to answer your question, these numbers, 11 can fit in a 4-bit number, 19 can fit in a 5-bit number. These are really small. I want P and Q to be 1024 bits. And again, if my seed starts small, yeah, I'll predict the initial output. But once we hit that modulus, the chances of it coming back down to 9 are 1 in 2 to the 2048.
Yes.
Right? So
But come to any small number, you can predict the next number.
sure. But those odds are so incredibly remote
Okay.
that you'll be lucky if you see that, I guess is what I'm saying. Yeah. All right. I need to watch the time. What time is it? How long do I have?
Technically, we have the room until 10, but. Normally, we try to cap it at 9.
Pardon?
You have 12 minutes left on the SD card.
12 minutes on the. Sorry, YouTube. You're going to be out of luck. Maybe we'll do that. All right. So here are some standards that are based on triple des and AES. These are more complex standards, but these are based on block ciphers. ANSI is a standards organization that creates standards in a number of different areas. And they created some random number generator based standards. ANSI X9.17 was based on triple des. It wasn't long before we said, triple des kind of sucks. So ANSI X9.31 replaced it with AES 128. But the idea is the same, and I'm going to show that here. This is the flow chart of either ANSI X9.17 or .31. All we're changing is the cipher. It's either AES or triple des, but the flow chart is identical. We're going, in the case of X9.31, we're going to take a 128-bit high precision timestamp of whatever the current time is. And we're going to create a 128-bit seed, 128-bit number. I'll encrypt my timestamp with AES, and it needs to be keyed. We can get that key from a password. We could get that key from, a number of different things. We're using this as a generator, so we'll assume I don't have a generator available to me, right? So we'll go ahead and start the seed at 0. We'll take the timestamp off the computer, and I'll build the key based off of some password. Okay? Then everything's fully deterministic. That's OK. We'll encrypt the timestamp. I'll exclusive OR that with the seed. Whatever that output is gets encrypted again. Okay, so the second time I make an encryption call, and that goes out to the application or to the user. But that output also gets exclusive OR'd with my encrypted timestamp. Whatever that result is gets encrypted, and that becomes the next seed. So I call the block cipher 3 times per request. I want a random number, AES gets called 3 times.
What good is something that has been randomized like that if you can't decrypt it on the other side?
So what good is it if I can't decrypt it on the other side? In this case, I'm using AES strictly for random numbers. I'm not using it to encrypt any data for the intent of decrypting it later. All I want is a random 128 bits. I don't care what they are, but it is 128 bits, so I can represent that as a base 10 number, right? Or a hexadecimal number or some other number. And I just send that to the application. I say, give me a random number between 0 and 2 to the 128. I go through that, something pops out, and here you go, here's your number. So I'm not interested in decrypting it, even though I'm doing encryption. All I'm using is the cryptographic properties of AES to give me those random numbers. Make sense? Mike?
Well, to some extent, you wouldn't want someone to be able to decrypt it because then that leaks the state of the machine, doesn't it?
Would decrypting it leak the state of the machine? No, because...
I guess you'd only get like maybe a small part of it, but not the entire
Yeah, you would, yeah. Guess you could undo it. Part of the reason we want our timestamp to be high precision is to make it somewhat unpredictable. Really hard to figure out what that timestamp is. Also, though, this key, whatever it is, should be the secret. That key is the secret. So I base it off of a password. So long as no one else knows that password, we're good to go. But if someone knows my password, this can be reconstructed. Okay? Now that timestamp's going to make things difficult, no doubt, but it's not outside of the realm of possibility, a practical possibility. All right. Turns out this approach, while it is prediction resistant, is not backtracking resistant. Remember those two properties? We nailed the first one. AES, just because of the cryptographic properties it has, will be unpredictable, provided you don't know the key. You don't know the key, we're good. But that design is not backtracking resistant. And if I think about it, why? If I compromise the state of this generator, how is it possible that I can generate past states?
Well, if you know what the seed is currently, you can run it back.
If I compromise the generator, I know everything here. I know the key, right? I know what the current seed is, I know the current output, but I also know the timestamp.
Because you can calculate that back.
Yeah, so I can just time how long is it taking, how many nanoseconds is it taking to calculate the output. I'm getting one every 5 nanoseconds, I don't know. So now I've got a delta to work my way backwards, right? I can go back every 5 nanoseconds, get those states. Now, the high precision timestamp will make things difficult. I'm still going to have a delta, right? Maybe plus or minus a nanosecond on either side, but I've got a small search space compared to the whole continuum. So that's the problem. The timestamp makes it not backtracking resistant. So it got obsoleted by a couple other standards. I'm not going to delve into them, but I started thinking about that. Could I improve on it? So my initial gut reaction was, let's take the timestamp out, because that's my problem, and let's put in some entropy, right? Maybe we can gather some raw entropy off of the computer, like timing keyboard strokes or mouse movements or network packets, right? Let's try and get some raw environmental noise, kind of pool that in some way and use that as my entropy. But if I have access to that, why am I even bothering with this approach? Why don't I just use that raw data to begin with? Because that's essentially true random data, right? Maybe give or take a little bit. So here is a better approach. This is designed by, well, I'll say popularized by Daniel J. Bernstein. He's a cryptographer that gave us Cha-Cha-20 and a lot of the elliptic curve stuff, and now he's big into quantum cryptography, post-quantum cryptography. But instead of 3 versions or 3 instances of AES, I'm only calling 1. So this is going to automatically be, a third the latency. What's the right term? The other one is 3 times slower, right? This is a third as slow. So we're going to take some password, we'll key it, however we do that, we'll get my key, right, based on the password. And then my application is going to say, I want 5 random numbers, 528-bit random numbers. This approach generates 6. So I say, I want 5. And it'll output 5, but it actually generates 6th. And it uses the 6th, the one that I don't need, as the next key. But all it's encrypting is just a counter. So next time I call it, if I say I want 5 random numbers, I just encrypt 1, 2, 3, 4, 5, 6. I give you the outputs of the encrypted 2, 3, 4, 5, and 6. But I use the encrypted 1 as the next key. Provided this initial password is secret and secure, this whole stack is secure, it's good. But if this ever gets leaked, the whole thing falls apart. But here's why it's backtracking resistant. This block is never sent to the application, never sent to the user. They never see it. AES gets rekeyed with whatever this is before the user sees that output, right? So if the state ever gets compromised, I'll know what the current block was, but I'll have no clue what the past blocks were that were used for previous keys. So I can't push that state backwards. And it's fully unpredictable because it's based on AES, and provided my passphrase is good, we're good to go. Make sense? So it's a pretty awesome little generator. Apologize for wiping my nose, it is itching. So, all right. Drives my wife nuts. We'll be driving and the vibrations of the road will tickle my nose. So I'll be driving, I'm constantly like batting my nose. She's like, I've never seen anyone be so concerned about their nose. I'm like, it tickles. I don't have any.
To us.
What?
You lied to us. That says Linux.
Yeah?
You said we wouldn't talk about.
Oh, fair. Ha ha ha. All right, touche. I'll give you a slide or two. Dev random. This is a special character device that was first introduced in the Linux kernel in version 1.3.30 by Theodore So in 1994. Linux was the very first operating system in the world to ship a cryptographically secure pseudorandom number generator as part of the OS. As a result of Linux in 94, everyone else followed suit. The BSDs, Windows, all the Unixes, like it was like, huh, that's a good idea, right? And then everyone followed suit. So that's kind of a fun little like bragging rights, if you will. Linux is better than Windows. We were the first ones with a random number generator. Like anyone will care. So it started based on MD5, but it wasn't long before we saw the problems with MD5. And so in version 2.1.104, he pulled out MD5 and put in SHA-1. And he based it on hashing functions for that exact reason, right? If SHA-1 ever gets broken, we could pull SHA-1 out and put in SHA-2 or whatever else is an appropriate secure hashing algorithm. But in 4.8, which came out, I think, in like October of 2016, he pulled out the entire thing and based it on SHA-20 instead. And the reason for doing that is SHA-1 is kind of slow. I mean, it's fine for hashing function, but it's kind of CPU heavy. SHA-20 is really light. If on my laptop, for example, when I was in 4.7, I could get about 20 megabytes per second out of the generator. In 4.8, I get about 300. Jitter, right? Power fluctuations, temperature. We have all these separate events that we can kind of pool together in a pool. And then we used to think that, oh, well, this is my true random data. So I send it through a randomness extractor, and that's what becomes dev random. But as I pool this stuff, I increment this counter. And as I pull data out of here, I decrement it. Okay? And when this approaches 0, then I stop giving output here. But as this goes up, I'm good to take data out of dev random. And then we thought, well, we have dev urandom. So after we've got my raw data, I put that as a seed into some pseudo-random number generator. And then that's just bad news. And we just have bad data coming out of dev urandom. That's not true. This is the correct architecture. We were right about the events. We're right about the entropy pool. We're right about increasing the counter when this fills up. And we are right about decrementing the counter when I'm requesting data from this device. So far, so good. The problem is, though, that after I've taken this data through the randomness extractor, it always gets fed into the cryptographically secure random number generator. And that output goes to both devices. The only difference is, when I pull off dev random, if this counter drops, like a gasoline tank goes to empty, my car stops. But this, I've got an electric battery with solar cells on the roof, and it's a bright, sunshiny day 24 days a week. Right? I'm good. This doesn't block. But the important thing is, both of it is giving me data out of this cryptographically secure random number generator. They're both based on a pseudo-random number generator. Okay? So now we got that straight, and everyone knows what 42 is, right?
Yeah.
Okay, all right. I was hoping you guys catch that. So here are some of the other operating system random number generators. Windows uses the standard CTR DRBG. This is defined by NIST. Mac OS and iOS use Yarrow. We discussed Linux. FreeBSD, OpenBSD, NetBSD. FreeBSD actually moved to SHA-20 very recently. So Linux and the BSDs all use SHA-20. Solaris, or any of the Lumos-based OSs, if you're still using that, uses HashDRBG, which is another one defined by NIST. All right, let's talk about a backdoored one. You guys ever heard of dual EC DRBG? Stands for dual elliptic curve. And then DRBG is the same thing as pseudo-random number generator, PRNG. It just stands for deterministic random bit generator. But it's the same thing as a pseudo-random number generator. So think of this as a dual elliptic curve pseudo-random number generator. Developed by the NSA in the early 2000s. 2004, NSA paid RSA Laboratories $10 million to include it in their algorithms, which included Secure ID, it included BSafe, some others, some core RSA products. What was interesting is this wasn't even really a standard. Like, the community started learning about it, and in 2005, cryptographers started voicing concerns about potential backdoors into the algorithm because some stuff just didn't seem clear and was a little fishy. Well, NIST, ANSI, and ISO all ignored those concerns and went ahead and standardized it. NIST standardized it in Special Publication 890A. ISO standardized it, ANSI standardized it, and then 2013, in June, Edward Snowden releases the NSA docs, and part of those documents was a project called Project Bull Run, which documented how the NSA, backdoored the algorithm and had every intention of breaking anything and everything they could. So if they could get in TLS, TLS would be broken. If we could get it, as we did in RSA, so on and so forth. So after those documents drop, NIST all of a sudden later says, hey, we didn't know this was backdoored. And all the cryptographers come up and say, garbage. We showed it to you. We emailed you. Here's all the emails. So NIST was like, oh, we're sorry. And then RSA said, oh, well, we'll stop using it, but we never got any $10 million despite the docs. And they're like, huh, well, here's the receipts. So yeah, that's not true. Eventually, long story short, it got pulled from ISO, it got pulled from NIST, it got pulled from ANSI. So it had a brief run from like 2005 to 2013, 2014, and then it was over. If you want to learn more about it, go to projectbullrun.org, and it'll tell you all the people who were involved. It'll give you a very specific timeline, all the documents, all the software that was compromised as a result. It's really quite a fun read. All right, wrap up with a few slides and then we'll call it good. Non-secure true randomness. Despite what you think, true random data is just biased. It is very, very, very difficult to take true random data and use that raw output in an unbiased manner. It is. And it's not necessarily a problem with the environment as much as our ability to sample it, okay, as much as our ability to put it together. We can look at true randomness two ways. We can either look at it via quantum entanglement, or we can look at it through chaotic noise. And there's a subtle difference. Chaos usually follows a deterministic pattern, but small changes in the initial seed represent large changes over the long term. Okay? Lightning strikes are chaotic. Photon spin is quantum. Okay? Now, we're going to split hairs again. Chaos is really the byproduct of quantum mechanics. Like, we could really get, I think that's as far down as we could go. But with quantum randomness, we're sampling micro things, where with chaotic randomness, we're sampling macro things, big stuff. Okay? Ultra randomness bias, just mentioned that. So here's an example. Let's take a beam splitter. Let's shine a light source, through a semi-transparent mirror. So it's either going to pass through or it'll reflect, right? It's semi-transparent. So either reflect or it'll pass through. And we'll put detectors on one side and on the other. So we'll detect passing through and we'll detect reflection. And we hit one, we sample a 0. We hit another, we sample a 1. Here's the problem though. Let's look at the breakdown. if this beam splitter isn't exactly 50% transparent, right? Let's say it's more transparent than it is reflective, I'm going to get maybe more ones than zeros. And the reverse, if it's more reflective than transparent, I'm going to get more zeros than ones. Also, I'll probably have some processor that's sampling the data as it's collected. Am I waiting for a bit to hit the processor and register it? Or am I saying, here's a stream of zeros, and as we hit the detector, insert the ones? So as you can see, it's difficult to make sure that I've got a good balance of zeros and ones in the output. I could try and approach this, I took the image out, with 2 light sources and 2 mirrors and 4 detectors, but I still run into the same problems. Atmospheric noise is a quantum process. This atmospheric noise is defined as noise on the 1 megahertz to 10 megahertz frequency range, and that's the byproduct of lightning strikes, actually. You'll get more noise closer to the 1 megahertz than the 10, but that's pretty much the full range of lightning strike noise. So if you ever, now you know, if you have a receiver, tune it in and listen to the noise, that's lightning strikes. But how do I sample the strike? Okay, here is the same strike, but sampled at different timestamps. Here I am zoomed in, here I am pulled out. Do I measure the strike as a bit, or do I get closer in? Like how do I measure what's a 1 and what's a 0? Like in this case, this could be a clear 1, and the rest of this is a stream of zeros. Maybe this is a little bit more 1s, more zeros, but how do I work this? Right? It's difficult. This isn't easy. So the way to do that is via what's called randomness extractors. By sending this biased true random data into a randomness extractor, I can get secure true random data. This will be suitable for cryptography. There are currently three known randomness extractors. I can use chaotic machines. There's a library out there called libchaos. It's on GitHub if you do a Google search. The problem with libchaos is this is a new field of mathematics. So it's not as well understood as cryptographic primitives like AES or hashing functions, or even von Neumann decorrelation, which is actually really quite slick. And the idea is that, okay, I've got my data, in the case of my beam splitter, but whatever that raw data is, I send it through the randomness extractor, and now I'm guaranteed to have unbiased, uniform output. That makes sense? So here I've got biased, non-uniform output, but after the randomness extractor, I've been able to smooth out that distribution, and I have a uniform distribution. So here's the GitHub link for the libchaos. It uses chaos theory as that randomness extractor, double pendulums, cellular automaton, chaotic maps, Brownian motion, those sorts of things. Cryptographic primitives, we've seen a couple examples of that with like the ANSI standard or the fast key erasure standard, where I use AES as my basically randomness extractor. I feed it in the data. I expect AES to be secure, so what comes out is uniform. But von Neumann decorrelation is probably my favorite of the bunch. And that is that we look at two consecutive non-overlapping bits. And if they're the same, we discard them. If they're different, we output the leading bit. Okay? So in this case, here is my biased data. I pair them up, right? 0, 0, 0, 0, 0, 1, 1, 0, 1, 0. And then I look, are they the same? Yep, they're discarded. The same, discarded. Different, I output the leading bit. Different, output the leading bit. So on and so forth, right? And this result is my extracted random data. Now automatically you're going to lose at least half of your data. That's clear, right? If every pair was different, then I'm extracting exactly half of the bits away. But based on how biased it is, it could be more. It could be even removing up to 2/3 of the bits or 3/4. Just depends on how badly biased the input source is. So that is kind of a bad attribute of the von Neumann decorrelation. There are some hardware random number generators that are included in CPU chips. Intel has RDRAND, which is included in their Ivy Bridge processors. Linux developers resisted strong urging by Intel to replace DevRandom with RDRAND. And Theodore So was like,
Why isn't it just sibling?
because Theodore So has this idea that entropy is like gasoline and that you use up entropy. But that's not the case. Entropy is more like a thermometer where it gauges the unpredictability of the state of the generator. So unfortunately, he's wrong in that regard. So he's holding on to it, I think, more for his pride than anything. But BSDs don't do it. iOS, Mac OS X doesn't do it. Windows doesn't do it. Linux is the only one that blocks on DevRandom. And it's a dumb design. And every cryptographer has bantered the kernel developers to stop doing it. And Theodore So just refuses to listen. So that's all. Mike.
I saw you listed as one of the things to seed or to improve your initial pool of entropy was to install HavHD.
Oh, yeah. I didn't mention
I
that.
also read that the HavH algorithm is somewhat contested and argued.
Yeah, it is.
And so what are your thoughts on it, on how secure it is?
All HavHD is pulling out more what's called CPU jitter off of basically the timings of the interrupts off the CPU that the kernel isn't doing. But it's important to note that when you're making the call off DevRandom or DevUrandom, you're not getting the raw HavHD data. It's still getting fed into the cryptographically secure generator, so you're getting the output of that result.
So it's no better or worse than, say, for example, the Intel
Right, RDRAND.
RDRAND.
Yep, you are no worse or necessarily no better in security by using HavHD or not using HavHD. In fact, as a joke, I'll tell people you could output dev0, which gives you an endless supply of binary zeros, and redirect that into DevRandom, and that'll consistently reseed the generator with dev0. But the generator also uses its own output as part of the next seed, and is completely and totally benign. You're not reducing the security, even though you're feeding it a constant stream of binary zeros. So you're okay. But there is a new kernel module called jitter entropy. It doesn't have the same performance as HavHD, but it's now in the mainline kernel. And you can just mod probe jitter entropy, and that'll handle that. You do need to run a user space service so it can actively collect stuff. But yep.
So really quickly, I was kind of perusing some languages and the algorithms they use, and JavaScript does use like the XOR shift.
XOR shift,
But some of them look a lot more confusing, and like even the C standard library didn't even look like it was using that. Is there any reason why those languages don't switch over to using those type of things for the random number generation?
So Mersenne Twister came out in '97, and because of its speed, like its performance, but also statistical quality, it just became a favorite really quickly. Kind of like a trend, like, you know. And people are happy with that, and it is a good generator. Even though there are better ones out there, it's like going from, you know, baby back ribs to buffalo wings. Like, I'd be happy with either. So I think we're seeing more efforts of shifting to XOR shift 128, but at the same time, it's one of those arguments where if it's not broken, why fix it? And I think that's a valid argument with trying to replace Mersenne Twister 1.9. Now, in the case of multiply with carry 1616, that had a legitimate bias problem. So there's a legitimate reason to replace that one. But Mersenne Twister doesn't have that concern. So unless you're really trying to squeeze more performance out with less state, yeah. Laziness, I guess. So, any others? Sorry to keep you so late.
It's been awesome.
But thanks.